Okay, so this is the problem we were working on last time. We were focusing on the translation in the S-axis transformations from going to T to S and then S back to T. And then here's the work that we've done so far. And we had a little Wolfram help. And now we're here. So what we've done, and the last thing that we did last time was we broke this up into these two pieces. Let me throw this negative sign over here just to make sure that it's accounted for. And then now I'm going to distribute the negative 1/2. And then now I'm going to be able to combine these two terms. So I'll circle it in red. This term and this term can get combined into one. I'm just trying to save space. So what do we have? We're going to have, let me rewrite everything over. Should probably write it in green. We got a 1/2 times 1 over S, which we can easily translate now. We have a minus 1/2 times S minus 1 over S minus 1 quantity squared plus 1. And now we have a positive 1 minus 1/2 with this denominator. So that would be a positive 1/2, right? And then that would be a 1, just a 1, over S minus 1 quantity squared plus 1. Okay, now, translating back, we have, let me put some of these transforms that we have. We have 1 over S, so that's just the constant 1. So let's take this back. L inverse. So I have a 1/2, and then S, the 1 over S is just a constant 1. For now, I'm going to put a times 1 there, which we can eventually drop. And then now I have a 1/2, and I have to try to figure out what goes in here, and then another positive 1/2 and try to figure out what goes in there. So let's see how S minus 1 over S minus 1 squared plus 1 translates. So that looks like a variable divided by the variable squared plus 1 squared. Which one is it? Cosine has a variable over the variable squared plus 1. K is equal to 1. Right? Why don't we come back. So looking at this transformation, there's a shift, right? There's a shift. So the shift is you're taking S, and then you're replacing it with S minus 1. You're taking S, and you're replacing it with S minus 1. So there's a 1 plus 1 shift to it. You see this plus 1? So the shift happens, sorry, I keep switching back and forth, but the shift happens when we take your shifted function in S back. It'll be the original function times the e to the whatever the shift was. Let's take a look at that. It's a shifted function in S. So we take it back as a cosine. K is equal to 1. cosine of t, and then the shift happened with a shift of a positive 1. So e to the positive 1 t. So that should be that transformation. All right, so we'll do the same thing. The transformation over here is going to be the sine function that's been shifted. So it's going to have the same shift, a shift of 1 in the s-axis means you got a factor of e to the t, and then 1 over s squared plus 1 is the sine t. Oh, remember that this was originally y, capital Y, so this must be y, little y. I don't know if we need to rewrite it. I'll rewrite it. So your final answer, y of t, is 1/2 minus 1/2 e to the t cosine t plus 1/2 e to the t sine t. So I think the trickiest parts in doing these problems in Laplace transforms is going back. So a lot of times you can easily transform into the S world, and certainly just a bunch of algebra. Now, the algebra that you might need to do might be some partial fractions algebra, so that's tricky, but nevertheless that's still algebra. And then now you need to jump back to the T world, and jumping back to the T world is when it gets a little tricky, because you're not using a transformation where you're integrating things, which you can do if you want, but we have a bunch of formulas that you just need to combine a certain way. All right, now that we've gotten through this problem, let's backtrack and see if we can practice inverse transforms, going from the S world to the T world with what you're given. And that also would involve this shifting in the s-axis. All right. I took some problems from the book, a bunch of these types of problems where, you know, you might have to complete squares, you might have to throw in the extra s minus 1 or plus 1 or whatever. So let's do 1 or 2 of these. Pick a number between 11 and 20. Anybody? 16. All right. So we're looking at 2s plus 5 over s squared plus 6s plus 34. Since the bottom is a quadratic already, this will most likely involve a sine and a cosine. And instead of breaking it up into partial fractions like we did, let's see if we can do something else. Let's see if we can complete the square and enforce the sine and cosine business to happen for us. All right, a quick lesson of completing the square. We have s squared plus 6s. I'll leave some space here, plus 34. And then I want to add something and subtract the same value, so essentially I'm adding 1. So if you remember, you take the b term, which is 6, you take half of that and square it. That would be 3, and then square it is 9. So I'm essentially adding a 9, so which means I have to subtract a 9, minus 9, over here. And then I would get a perfect square as a result, because I forced it to be, and then whatever this turns out to be, 25. All right, so that's the completing the square business. I hope you guys are good at it, or at least capable of it. And then now let's take this and then break it up, break the numerator up. I have a shift of -3 here. This is s minus -3. So I want to do something with the numerator that would reflect that shift. Okay, so I worked with the denominator. Now I'm going to work with the numerator, 2s plus 5. I want to force a +3 here. Now this is going to be tricky with a 2 here, but let's see if we can manage. So just like the completing the square business, where I want to add something inside and then subtract the same thing so I don't change the value. When we did our example in that problem, I just added a 1, subtracted a 1, so that wasn't a big deal. This is a little trickier because you have a coefficient of s. So what I want to do is I want to add something in here. Well, no, I want to add 3 specifically in here. Let's do this in a different color. I want to add 3 in there, and so I would need to subtract 3. I really added a 6, right? So I want to subtract the 6. And that 6 comes from the 2 times 3 that you really added. You really added a 2 times 3 in there. And if you want, you can go ahead and simplify this, you know, distribute, multiply, and then cancel things out, and you'll see 2s plus 5. All right, now we're ready to rewrite this fraction. Let's rewrite the fraction as 2s plus, well, no, let me rewrite it the way we have it written over here. 2s plus 3, what's 5? This is -1, right? Over s plus 3 quantity squared plus 25. So I'll break this up to 2 different fractions. 2, let me write the 2 out here, and then I have s plus 3 over s plus 3 squared plus 5 squared, just to try to make it look like that. Now, I have a -1 over s plus 3 quantity squared plus 25. Now, this second fraction isn't quite what I want. Remember, when you're looking at, when you're integrating, you do use substitution to make it look just like, exactly like one of the first 9 integrals that you learned to do. Everything else with some form of substitution type technique, will make it look like one of those first 9 integrals. And so what we want to do is we want to make it look exactly like one of these transformations. Now, the constant over the fraction, the quadratic over here, that would be d. That one has a k in the numerator, right? So what you want to do is you want to force a k in the numerator. Well, what's k equal to in our case? K is equal to 5 in our case, right? So we want to force a k in the numerator, which means if we're going to do something in the numerator or do something in the denominator, it's not going to change our expression. So we're going to make this into a 5, but let's divide by 5 as well so that we don't change our expression. So now your constant that used to be 1 or -1 is now actually a -1/5, so that you have a matching constant numerator that you need it to be. And once you do that, and it looks exactly like these two expressions. So one of them the constant one becomes a sine, the variable one becomes a cosine. So let's write it now. Back doing our inverse Laplace step, we have a 2, a constant, and then you have s plus 3 over s plus 3 squared plus 5. So k is equal to 5 in this case, and a, our shift, is equal to -3. So we have e to the -3t as our shifting compensation for a shift, and then this is the cosine 5t. Okay, and then the second one, there's a shift again, and then this time a constant, now with matching power, or matching k's. The k is equal to 5, and the k is the coefficient of the angle, so that's sine 5t. Okay? So those are the tricks that you need to learn, at least so far, with dealing with a shift in the s. So this idea that you might complete the square, idea that you might add and subtract the same thing. Be careful when you're adding and subtracting things with coefficient. And then this idea that you might have to, multiply and divide by the same number to match up with the k. Okay? You want to be able to do this. You can, right? This is all algebra. It's algebra that we don't talk about because the idea of adding 0 or multiplying by 1, that's really what we're doing. That idea doesn't fly well with somebody who's just learning algebra. Why would you add 0? Or why would you multiply by 1? But there's the reason. If 1 looks like 5 over 5, it would sure help here in this case. So I think this is good. We can do another problem if you want, or we can move on. Are we good? You think you guys are okay with this? You're guaranteed to run into this in the future. 20. Let's take a look at 20. I hope I can do 20. All right. So when you're looking at an S expression, what you want to do is you want to always have this handy. Maybe you need to put this in a little index card. Just have it in your back pocket and look at it whenever you need to. And you want to try to see what function would be available for something like this. And I'm looking at this, these ones with the sines and cosines with the trig functions, doesn't look like it'll fly, it'll work. Even the exponential function over here doesn't look like it'll work because this looks like it's a shift. But now it looks like there's a shift on top and shift in the bottom, so this looks even stranger. So my suggestion here would be to do some sort of expansion. I don't know if this is the best approach to do this, but to do some sort of expansion into the partial fractions and different partial fractions that you get. So this time let's try to do this without using Wolfram. I'll try to refrain from using Mathematica and see if we can actually do this by hand. So my idea is to write this as not the L part, but just the fraction part, as some. Now this is s plus 2, a linear term that's raised to the 4th power, and so this is a linear term with multiplicity 4, which means your numerator should just be constants. So I would write it like this. And then whenever you have something with multiplicity more than 1, you can repeat that multiplicity with consecutively higher and higher powers. And then for each of these, you can deal with this as a shifting Laplace inverse. So if we can find A, B, C, and D, then we're all set. So let's see if we can find it. So I would probably multiply by s plus 2 to the 4th power, and on the other side of the equal sign, I would just be looking at the fraction. And so if I multiply by s plus 2 to the 4th power, I would just have s plus 1 squared, which I'm going to eventually multiply out, is equal to, now I multiply everything by s plus 2 to the 4th power, I'm going to have a times s plus 3 to the 3rd, because one of them will cancel, s plus 2, I don't know where 3 came from, b s plus 2 squared, and then c s plus 2, and then d. I suppose I should have foiled this out now, or before, but I'm going to FOIL it out now, so that's s squared plus 2s plus 1. So in doing the partial fractions, I would try to see if I can match up the coefficients. Let's see if I can match the coefficients. Now, this is going to be a little bit messy. Let's go with the mess here. I need to multiply this 3 times, FOIL it out 3 times. You could do this by hand, or you can remember the formula for a binomial. I think the formula is s cubed plus, trying to remember my Pascal's triangle. Is it 3? 3s squared plus 3s again, or 6? How many terms am I going to have here? 4. So there'll just be 3s plus, oh, no. All right, I guess I don't know my formula. 3 times 2 s plus 3 times 2 times 2 is 4. Oh, this is squared. Plus 8. Yeah? All right. So, if you don't know that formula off the top of your head, apparently I did, you could just multiply this 3 times. So you multiply s plus 2 times s plus 2, and then you'll have 3 terms, quadratic, and then multiply that with s plus 2, and then you'll eventually get this. All right, the b is going to be s squared plus 2 plus 2, 4, plus 4s plus 4, and then I have c s plus 2. Now FOIL now, or now let's distribute later, plus d. All right. Now I want to start combining, see if I can combine terms. I have a s cubed. That's my only term with a cube. Now let's see if I can collect all the terms with an s squared. I have A, 6A, and B. Those are the ones with an S squared. So all the ones with an S. I have 3 times 4 is 12 times A is 12A times S, which I'll factor out. I have a 4 times B, positive, and then I have a C. All this is multiplied by S. And then all the other constant terms here would be 8A plus 4B plus 2C plus D. So this is the constant. All right, set them all equal to 0 times S cubed plus 1 times S squared plus 2 times S plus 1. So A is equal to 0. (6A plus B) is equal to 1. So A is equal to 0, so B is equal to 1. (12A plus 4B plus C equal to 2. Well, A is equal to 0, B is equal to 1, so I have 4 plus C equals 2, so C equals negative 2. And then 8A plus 4B plus 2C plus D equals what? Equals what? Equals 1. That's the constant on this one. So that's equal to 1. We know that A is equal to 0, B is equal to 1, C is equal to negative 2, and we're solving for D. So we got 4 minus 4 plus D equal 1, D equals 1. All right, so when you have these repeated roots in the denominator, this is when you're not going to be able to use the little, just substitute, let S equal to 2 or something like that. Because if you let S equal to 2, then a whole bunch of stuff disappears. When you let S is equal to 2, you can solve for D, by the way. But we'll need to solve for a few other variables, so might as well go through it the long way. All right, now that we've done that, we know that we're really looking for the L inverse of A, well, 0, let's just ignore that, plus B over S plus 2 squared. So B is 1. C over S plus 2 cubed. So I'm going to put a negative 2 over here and keep the 1. Oh. Those things have factorials on top. Picture. Oh. This is our key formula. Where should we put it? Right here? Which means I need to match up an n over here. So in this case, I have to the second power, so n is equal to what? Looks like n is equal to 2, or n is equal to 1. So that's a 1 factorial, so that's okay. Over here, n is equal to 3. Or no, the power is equal to 3. So what does n equal to? N is equal to 2. So I need a 2 factorial up on top. You see that? How am I going to get a 2 factorial up on top? Just multiply it by 2. Oh, yeah, I already have a 2 there. Oh, yeah, I suppose. Save money. Let's put that 2 over there. All right. I think it will make more of a difference in our last one. D is equal to 1. That's our last one, right? So D is equal to 1. We have a 1 over plus 1 over s plus 2 to the 4th power. And this one, n is equal to 3. So I want a 3 factorial on top. Now, what do we do? Multiply by 3 factorial, divide by 3 factorial. I guess that's 6, right? So there you go. Well, there you go, almost. So back in our real world, we have a shift. We have a t to the n is equal to 1, t to the 1st power with a shift. So that the shift is what? What's our shift? Minus 2. Our shift is negative 2. So our shift is negative 2. When we take it back to the real world, it's an exponential function. Minus 2t times t just by itself. And then I have a minus, and then this time I have I still have a shift of negative 2, but this time I have n is equal to 2, so that's t squared. And this is the one where I get that extra constant, 1/6, that I needed to pull so that I can get that 3 factorial up on top. And now I have this as this formula with n is equal to 3. So that would just be t cubed. Oops, don't forget the shift. Shift is e to the negative 2t. That compensates for the shift in the s world. And now we have t to the 3rd power. Okay. So it was unfortunate at the very beginning that I had an s plus 1 and s plus 2, and so those pluses didn't match. And so I needed to do something else. I knew that my denominator is just a plain and simple s with a shift, s to some power with a shift. And so I got my eye on this thing. It wasn't s squared plus something else or s squared minus something else. It wasn't a quadratic in the bottom where I need to complete the square. You have to be able to look at this problem where it says s plus 2 to the 4th power. You have to think about that as not a 4th degree polynomial, but a linear term, s plus 2, with multiplicity 4, raised to the 4th power. So it's not a 4th degree polynomial that you can't reduce because you're able to find linear terms for it. Okay? Phew. How's it going so far? It's all algebra. Yeah. Because of the shift. This is our shift. Which one should we do? I think if we just do this one. So this formula allows us to do the shifting. And so when we have an s minus a, in this case s minus -2, that translates back into the t world as e to the -2t. Okay? Looks weird, huh? So that's the tricky part. Oh wait, there's more tricky parts. Okay, ready for more? So we did the shifting in the s-axis, but there's a shift in the t-axis that's also possible. So imagine, and we could always take our problems from the spring problem. So imagine you have a spring, and then it's oscillating, and imagine that there's an external force that moves this, but doesn't do it forever. So imagine there's an external force that moves this for a certain amount of time, or maybe that doesn't move it, and then later on it starts pushing it around. So it's possible that we can have a system with an appropriate, second order differential equation. That might not do anything to the system, to the spring, and then later on it puts on an external force. So they introduce a new function called the step function, or sometimes called the Heaviside function. I just drew it right here. Oh, that's a step function. All right, I can go back to my notes now. So this is called the Heaviside function. Not because it's heavy on one side, but because they actually named it after a guy named Heaviside. So this is called the Heaviside function. And what we need to do is, it's a lot of times it's easy to graph these things, but it's a little bit trickier to write it in terms of functions and formulas. And so they introduce this function called U, called a unit step function, capital U. And it's based on a shift where it's 0 for most of the time, and, well, not most, but it's 0 for some of the time, and it's equal to 1 for the other time. And in general, we want to look at this for positive t values, and so we just define it from 0 to infinity. So here it's going to be 0 from time 0 to time a, whatever a is, and then at time a, it gets turned on, so you turn it on, and then it does whatever it's going to do. So by being able to write it as a function like this, a closed form function, instead of writing a piecewise function all the time, because we're doing Laplace transforms, we have to be able to look at function-wise. So it's important to define a function like this, and then talk about how to transform that using a Laplace transform. And so how would you transform this? I don't want to do the integral proof of this, but that's how you would normally do it. I don't know if the book does it. I didn't look. But you can start it by, I'm not going to complete this whole thing, but the Laplace transform of the Heaviside function, make your u look a little fancy, is going to be, by definition, this is equal to the integral from 0 to infinity of e to the negative st times the u, not mu, but u of t minus a dt. Now, this is equal to 0 from 0 to a. So this has no contributions for all these values, and then now you just start from a to infinity of e to the negative st dt. And since u is equal to 1 when t is bigger than 1, I just have a 1 here that you can't really see, but there's a 1 there. And so whatever this turns out to be is going to be a result. That turns out to be e to the something. So we add one more to our list of Laplace transforms. So now we have a Laplace transform for the unit step. In general, we don't just want a unit step. We don't just turn something on to have a function 1. In general, you have another function associated with it. So if we go back to our example, by the way, before we do that, you know the graph of this, right? The graph is 0 up to a, whatever a is, and then it jumps up to 1. I guess one of these holes is filled in. Let's fill in the top one. Doesn't matter. But it's a step function. So in general, we don't want it to just step up to 1. In general, we want it to step up into a function, right? So let's take a look at this function that I wrote over here where f of t is equal to 0 t. So how would we write this as a step function with u? So f of t in this case is going to equal to, I know I have a shift of u, it's going to be 0 everywhere else, so I know that this is going to be a u of t minus 2, a shift of 2. But after 2, it doesn't just become 1, right? It becomes t. So what should I do? You understand my question? Are you with me? No? Where did I lose you? In the beginning of class? So, any suggestions? Christopher, you want to say something? Say. So this is my step function defined as u t minus a, 0 from 0 to a, and then 1 from anything bigger than 2. So if my a is equal to 2, this is a good function for it, but this does not exactly equal to this. What do I need to change, or what do I need to do to this? By what? By t, yeah. If I just multiply this by t, 0 times t is 0. I should be pointing here. 0 times t is 0, and 0 times 1 is t. And then this would be exactly that function. Okay? So now, instead of writing it as a piecewise function with two pieces like this, I can use my unit step function, and now I can rewrite my function as a unit step function times t. Okay? Well, if this was sine, then you just replace it with a sine. It gets trickier if you want it to be something and then 0 after that. But there's formulas for that as well.
So if it's 0 and set it like a function, will that change the u of?
Yeah, it'll change it slightly. But I don't want to think through the process of that, so let's just get the formulas. There are formulas for that. So if I didn't start with 0, if I started with a sine or a cosine or something, and then I decided I wanted to stop, because that's possible. You got this spring, you hook it up to a machine, and the machine is some function like sine or cosine, and after 10 seconds you stop it. So now the spring is on its own, and what's going to happen? So that's another scenario, and that for that particular scenario you have a function from 0 to a particular value, and then you replace it with another function after that particular value. So here is your more general formula that uses a stepwise, the piecewise function. So let me copy it and put it in our notes and look at it, stare at it, and then do some examples where we have some functions that get replaced. So for example, what if we had a function that moves with a sine and a cosine, or sine, just a sine, sine t from 0 to pi, and then after that we turn off that machine, and then so what's going to happen to our object after pi time t? So the function becomes the first function from 0 to whatever minus that function times the u of t, and then plus the second function. So you kind of start by turning it on with the first function, and then you turn it off, you switch everything off, so you subtract that function off at a particular point, at a particular time, a. And then now you turn it on with another function called h. So if we have f of t that looks like this, how can I write my f of t as a one-line function, a closed-form function, instead of this piecewise function in pieces? Well, that's just sine t, looks like, minus sine t u of t minus pi plus, well, that's just h is 0, so that's just 0 contribution, so that's it. So this is going to be my function, sine t minus sine t times the Heaviside function shifted at pi. That's going to be the way I can write this. And then I can transform this. There's a linear transformation for this. Wait, there isn't yet. There was just the linear transformation was just for the u, right? So let's figure out what the linear transformation of a function times u is equal to. But for now, is this good? Is this okay? By the way, you know what the graph of this is going to look like, right? The graph is also important. You should be able to graph these things. So the graph of this, I think, sine is on 0 to pi, and the sine stops here at pi, and then after that it just becomes 0. What if if we switch it around, then that's kind of the same boring thing. What if we have a sine and then something else, or a cosine? Let's start with a cosine. Let's do another one. Say your f of t is equal to, let's say it's a cosine function from 0 to 2, and then after that it becomes a linear function, and I'm going to write it as t minus 2 when t is bigger than 2. So the graph of that might look like this. It's a cosine function up to 2. Oh, where's 2? 2 is less than pi. It's bigger than pi over 2, right? So it's going to go past here, right? Not all the way down. So it's going to stop somewhere over here. And then at some point, t minus 2, so that's t function, and then shifted 2 down. So I think it's going to hit here at 2. Then it'll go up like that. Hole somewhere. So you'll have combinations of functions like this. So how would we write this? Let's write this using the Heaviside function. And it's just a formula now at this point, right? So we don't even have to think about it. So that's cosine t. Of course you should try to think about it on your own. Minus cosine t times the shift, the u, the Heaviside function, plus, and this time I have a t minus 2 times the Heaviside function. Okay. So this is the this constitutes the shift in the t-axis. And that's happening in the real world. So physically, that could be a machine that's moving, and then you turn it off, or you change the machine function into something else. This one starts off with a cosine function, and then you switch a lever, and it becomes a t minus 2. Or this one is a sine function, and then after time pi, you turn it off. And then so whatever your system is doing is going to do whatever it's going to do. All right. So now that we have these types of functions to deal with, we want to transform them, Laplace transform them into the S world. And so how can we do that? So we need a formula for that. And again, instead of, here it goes. So instead of doing the, what was I going to say? Instead of doing the integral to prove this, I'm just going to tell you what it is. And here's what it is. So the tricky part about this is that you're doing a transformation for the u, but you're also going to want your function shifted. So that's probably going to be the tricky part. I probably gave some not so good examples with sines and cosines, so it might be better if we dive into the book and take a look at some examples that they have there. But if this function isn't already shifted, then you have to force a shift the same way we forced the shift in the s. You know, we had an s over s minus 1 squared in the bottom, some stuff like that. And so we wanted an s minus 1 up on top, so we subtract 1 and you add 1. So it's going to be the same sort of story happening here. Well, let's take a look at this, though. It's kind of weird because we've been dealing with the s world with just s's with fractions. And now with a shift in the t-axis, we're going to get introduced to an e to the minus as in the s world. So how are we going to deal with that? Well, the way we're going to deal with that is that we're going to take this, and that's just going to be around in our algebra work, and that's going to be something that we're going to factor. And when we take it back to the real world, from the s world to the real world, our result will also have a shift in it. And that makes sense because we shifted, and so our closed form function isn't going to be a nice function all the way through. There's going to be some shifting when we take it back to the real world. If you understood what that meant. In other words, if your original problem had a shift in it, then your answer is probably also going to have a shift in it. That's what I was trying to say. All right, I suppose we should practice first before diving into a problem. And I don't think I copied any warm-up problems here. So, do I have the book open? I don't have the book open. The internet is slow. Yeah. I'm going to pull the book, my copy of the book. All right, let's see. Let's do some transforms. I have some missing things here. I don't know what they are. Maybe this is a pirated copy. All right, let's do a few of these. Let's do number 38. So it's going to be important that you start getting used to being able to find these values here. So according to my formula, I want the f with a t minus 2, and this is 2 minus t, so that's off by a negative sign. So maybe I can just rewrite this as e to the negative parentheses t minus 2 times the step function. All right, so this is an L transformation, which means I'm taking things from the t world to the s world, so my answer should have s's in it. Now this is a translation in the t, so my final, my s result will have an e to the as. A is equal to what in this case? Two or negative 2? 2? Oh, but the transformation has a negative anyways, right? As if it wasn't confusing enough. So this is your transformation. A is t minus a, you're taking a and then you're putting a negative in front of it, so e to the negative as. And then now I want to look at e to the, I have to look at this as e to the negative t. What's the transform of e to the negative t? What's the transform of e to the negative t? One over s. No. 1 over s plus what? Okay, so if we look at this carefully, what do we need to see? We need to see this. So f of t minus a, right? So let me rewrite the problem. Was it e to the 2 minus t times the step t minus a? So I rewrote this as f to the negative parentheses t minus 2. Right? So I need to identify the values that I have here. I have a is equal to 2. Right? So in my transformation into the s world, I'm going to have e to the negative 2s, right? That's e to the negative 2s, because a is equal to 2. Now my function, my f function, let me write f of t minus a equals e to the negative t minus 2. A is equal to 2, so let me just write 2 in this case. Right? And so one thing to think about, or if this is really confusing, one thing you can do is you can replace this t minus a as x. So now in your transformation, you're looking at the f function itself, which is e to the negative x. And in the f function, that translates into, if you take the Laplace of this, this is 1 over s minus negative 1. So there's an a here, but this is a different a that you're dealing with when you're doing the transformation here. So this negative 1 is that negative 1 down there, which is different from the 2, which is the shift. Okay? So back to our problem. This is how it should have worked. Okay? I wanted to get through this already. All right. Oh, yeah, this should be an S. Thank you. Let's do one more real quick. So this one is a 3t plus 1, but you want a t minus 1, right? So you could pull a 3 out if you want, but you want a t minus 1 in there. So we'll do that thing where we have t plus 1 or 3t plus 1, and then we'll add 0 to it. And then we'll think about splitting this up to two different pieces. So what are we going to add? We want to add 1, or add a minus 1. So we're adding a negative 3 essentially, so we have to add a positive 3 here. So 3t plus 1 becomes 3t minus 1, or 3 parentheses t minus 1 plus 4. And again, if you simplify this, you should get 3t plus 1. My u's are starting to get sloppy. So u t minus 1 is what you have here. You're trying to find the transform of this. So for this, I might be interested in splitting this up. 3 t minus 1 times u t minus 1 plus 4 u t minus 1. So now I have the transform of something, whether it's t minus 1. So what's the transform of that? So I have a 3, and then what's the transform of just t? Remember what the transform of t is? 1 over s? 1 over s? 1 over s squared? Oh, there's a shift, right? E to the, what was the shift? E to the negative s. The shift is 1. It's negative as, so negative 1s, so negative s. E to the negative s is your shift. And then you have a 4. And then what's the transform of 1? That's 1 over s. Yeah? No, the negative should be there, because the formula says negative as. So a is so you have t minus 1, so this would be negative 1 because it's a minus 1. So I guess what you could do is just remember these two have the same signs. I don't know if that's helpful, because it seems a little bit more confusing the way we're explaining it. But that's how these two will. That's how this transforms to two terms in your S world. All right? Oh, we're way past. Okay. I was thinking about giving you guys a quiz over the weekend again, take-home quiz. Is that cool? Instead of taking a quiz here next week on Tuesday. So I'll post it up online, and then it'll be some Laplace transform problem. Yeah? Due on Tuesday, yeah. I'll send you, I'll post it as an email again like last time.